Okay, chapter 10, lecture 3, almost done. Hang in there, 2 more lectures and we are done, and then it's just a couple of exams in 3 days, and here comes summer too. Okay, so here's a rather involved word problem. Let's read through it and then figure out what's going on and see how we can solve it. And that's exactly what you're going to have to be doing on your own when you are confronted with these little deals here, right? So here we have a pure volatile liquid, and we are placing it into a 100 milliliter flask, and we are told the mass of that flask, and then it is placed in boiling water. Okay, so we are taking a liquid, we have it inside of a flask. Okay, that's an Erlenmeyer flask. We probably have it sealed. It doesn't say there. We have it sealed, put a tiny little hole there. And then you place it, and it's volatile, which means its boiling point is probably less than that of boiling water, right? So if you submerge that into boiling water, then these particles are going to, the liquid's going to turn into a gas. It's going to fill up the flask, and at some point it's going to stop expanding, and some of the excess pressure will go through, and so this flask will be filled. And we know it's going to be the temperature of the gas inside is going to be the temperature of the boiling water, right? So that makes sense. So we do that, and then they also tell you the barometric pressure is 751 torr. So we know the volume of the flask, which is going to be, we're going to assume that the volume of the flask is going to be equal to the volume of the gas. So we know it. And then we have temperature, we know R, we know volume, and we're given pressure. Okay? So I guess we can use the ideal gas constant to solve for N. Now let's continue reading, right? The flask was removed and allowed to cool, the volatile liquid condensing, and its mass was determined to be 90.43 grams. Okay, so this is now the flask with the liquid minus the empty flask will give us the mass of the liquid, which was a gas. So that in a way would be the mass of the gas at 100 degrees, a volume of 125 milliliters, and a pressure of 751 torr. Okay, and so the question is, what is the molecular weight of the liquid? And we used to do this in the lab. It's kind of fun, but it's not exactly something we can do at home. So let's work through this here, right? So we have PV equals nRT. We can solve for N, but you know we're going to have to substitute to solve for molecular weight. All right. So if I have molecular weight equals mass over moles, we can substitute again into this PV equals nRT and solve for N, right? So we can say that N is going to be equal to Vp times V over R times T. All right. Well, we could substitute. We can also work it separately. So let's just do it that way, right? Okay. So I know that the temperature, we'll need this later. I know that the temperature is equal to 100 degrees, which is 373 K, right? Ideal gas constant is in ATM K, and so we have to convert every single thing, including the volume, which is 125 milliliters, so it's going to be 0.125 liters. The pressure was given in torr, 751 torr, so you divide that by 760 and get 0.988 ATM. And then we know what we also know, it does not go into this formula here, is we know the mass, which is that 90.43 minus 89.56. So the mass of the liquid is 0.87 gram. And again, that's going to be equal to the mass of the gas. Okay, so we can calculate the molecular weight by determining N from this formula, and by knowing mass. So you can just simply do it that way, right? So let's plug this in. So we have 0.988 ATM times 0.0125 liters divided by ideal gas constant 0.0821 liters atmospheres degree Kelvin mole, and then the temperature 373 Kelvin. Kelvin cancels. I forgot to put, this is a liter here. The liter cancels, the ATM cancels, and this is 1 divided by 1 divided by moles, so the answer is going to be in moles. My answer is 0.00403 moles. And again, we plug that into here, so the molecular weight is equal to 0.87 grams of stuff divided by moles, 0.00403 moles equals 116 grams per mole. Question answered. Okay, so here it is nicely worked out. You have to convert everything to the units of the ideal gas constant. So everything I gave you needed to be converted, milliliters to liters, torr to ATM, and then the temperature we got from the boiling temperature of water. Okay. Alright, so let's take a look at chemical reactions and how they relate to the gas laws, or can, right? So here we have a reaction of calcium carbide that's reacting with water, and neither one of those are gases, but what's happening here is we are producing a gas. We are producing ethene gas, or acetylene, ethine gas, and if you draw the Lewis structure, it's going to be like that. And alright, and so the question is, calculate the volume in liters of acetylene produced at 26 degrees Celsius, 684 millimeter mercury from 0.05 moles of calcium carbide. So that's not the moles of the gas. However, it's related to the moles of the gas by the coefficients from the balanced equation. And in this case, it happens to be 1 to 1, because for every mole of calcium carbide produced, you produce 1 mole of gas. So that's an important fact that we need to carry with us when we do this problem, right? So we can actually use PV equals nRT, and using this conversion factor here to plug in for N, right? So we are asked for volume, so it's PV equals nRT, and I'm not 100% sure if I have a blank space here, so I'm just going to bring it up, but it's not a big deal. It's just PV equals nRT solved for V. The number of moles of calcium carbide in this case is in a 1 to 1 ratio, so we can just plug that in for acetylene. Ideal gas constant, temperature has to be converted, 26 plus 273, and then this has to be, of course, millimeter mercury is like torr. So 684 millimeter mercury divided by 760 millimeter mercury equals 1 ATM. You get 0.9 ATM and a volume of 1.36 liters, right? So it's not always going to be 1 to 1. So you always have to look at the balanced reaction before you can do this. Alright, so let's take a look at another one. Same concept here, right? Nitric acid is produced from nitrogen oxide, NO, nitrogen monoxide, which in turn is prepared by the Ostwald process. Okay, so this is the production of nitrogen monoxide here from ammonia and oxygen gas. If 2.7 liters of nitrogen monoxide are produced in the reaction at 26 degrees Celsius and 720 millimeter mercury, how many grams of ammonia were used up in the reaction, assuming oxygen is in excess? Okay, so we are looking at the relationship between ammonia and NO, and they happen to be in a 1-to-1 relationship. So for every 1 liter of ammonia that you use up, you are going to produce 1 liter of nitrogen monoxide. So that's the one relationship, right? That's important to note. So you know that 4 moles of NO equals 4 moles of NH3. And then it's going to ask us for how many grams. So we're also going to need that the molecular weight of ammonia. And that's, of course, 17.03 grams per mole. So the trick here is to use the conditions for NO, for N, solve that, and then use the molecular weight of ammonia because they are in the same relationship. And so we can again substitute N here for grams over molecular weight, and PV equals nRT, and then solve for G. So when we do that, we have G equals 0.947 ATM, right? Forget that. Let's just do the algebra. PV equals nRT. We take this and substitute it. Okay, so this is coming out. So you have grams per molecular weight, and then we solve for G. So you divide by RT and you multiply by MW. And I'm just going to go to the next page where that's worked out. So this is where this equation comes from. ATM had to be converted to millimeter mercury. Sorry, the millimeter mercury to ATM, and then the volume was in liters, so that was good. We are asking, we want to know the grams of ammonia, so we use its molecular weight, and then ideal gas constant, and of course 26 degrees is 299 K, and we end up with 1.77 grams of ammonia. So it's important that you look at the balanced equation and make the connection there, right? And sometimes it's a solid or a gas, and you just have to put the pieces together. It's part of science. Shifting gears just slightly, fairly simple concept here. It actually turns out if you have a mixture of gases that you can calculate and partial pressures of these gases and apply them to individually to to the ideal gas law, right? So if you have, let's make it simple, you have a 50-50 mixture of nitrogen and oxygen gas, right? So you put this in this flask, it's sealed, and this flask is at 1 ATM. If you have exactly a 50-50 mixture of it, then the partial pressure of nitrogen is equal to 0.5 ATM. And the partial pressure of oxygen is equal to 0.5 ATM here, right? If A was N2 and B and we didn't have C, and therefore 0.5 plus 0.5 equals the total pressure here, which is 1 ATM. We can take that even further, and well, first, before we take that further, it relates, okay, so the partial pressures here are also related to their percents. This is just to show you the air is made up of 78% nitrogen, 21% oxygen roughly, and then you've got all the other gases in there, argon and carbon dioxide and some other gases. It's not very much, right? Those are the percents. More importantly, the percents which are part, of course, divided by total times 100. If you leave the times 100 out, that would be just a fraction, right? And so a pressure fraction and a mole fraction would be here, kind of like that. So the mole fraction is equal to the pressure fraction, right? So if we go back to the the 50-50 mixture of nitrogen and oxygen, we can say that if it's 50% oxygen, or the mole the mole fraction is 0.5, right? Because 50% has a fraction of 0.5 without the 100, right? Multiply that by 100, you get your 50. So if that was the mole fraction, then that would be equal to the pressure fraction here, right? So if 0.5 atm would be the equivalent to 0.5 moles. And we can use that in some reactions, where not reactions but mixtures of gases, to determine the individual pressures and volumes of the components, right? So a problem like this becomes pretty simple then. A 4-liter flask contains 5.65 grams of nitrogen and 1.76 grams of oxygen. So we have a mixture of two different gases here together, and we don't know if it's 1-to-1 or 1-to-3, but we can determine that looking at the ideal gas law, right? And we know the masses, so we can figure out the the mole fractions, which are going to be equal to the pressure fractions, right? And so this is together in a flask. Again, I'm going to try to draw an Erlenmeyer flask, and here we have a mixture. And so the mixture has a total temperature of 25 degrees. And what it's asking for, and this is a 4-liter, so we know its volume. And so we want to know what the partial pressures are of each gas. And so on the way there, we need to, of course, figure out the total pressure. And if we want to know the number of moles, which is PV equals nRT, right? PV equals nRT. We don't know what N is, but we can certainly use the masses and the molecular weights to figure that one out, right? So one of the first things I would do is I would figure out the total pressure by using at the mole fractions. So you take the 5.65 grams of nitrogen and you figure out how many moles there are, times 1 mole divided by 28.01 grams per mole equals 0. Oh, sorry, it's not per mole. This is already written correctly. 0.202 moles of N2. And I can actually use this number of moles and plug it into PV equals nRT with these conditions to figure out the partial pressure of nitrogen. I can do that. That's one way to do it. I'm going to show you a different way. I'm going to do the same thing with oxygen here. Of O2 times 1 mole of O2 divided by 32 grams. I get a partial pressure of 0.055 moles of O2. Again, I can use that and plug it into PV equals nRT. They're both gases, although contained together in the flask, are under these conditions, 25 Celsius and 4 liters, right? Okay, so the total pressure here is 0.257 moles. I just add that up, right? And so the mole fraction is actually going to be equal to the pressure fraction, right? So if I have, and I can then calculate 0.202 moles of N2 divided by 0.055, sorry, it's total, of course, 2.57 pressure moles total. That gives me a mole fraction, and that mole fraction is going to be equal to the pressure fraction, okay? So the pressure of nitrogen over the total pressure. Alright, so I can get the total pressure by using PV equals nRT. So P total equals 0.257 moles times 0.0821 liters times atmospheres per degree Kelvin per mole times 298 degrees Kelvin, right? 273 here, right? That just converted, divided by the 4 liters. That gives me a total pressure of 1.57. So I can take this mole fraction and just multiply it by the total pressure, right? Which is 1.57. And so I get 1.2, that's a 2, 3 ATM. If I do the same thing with oxygen, and I'm running out of space, but so I just do the same thing here and multiply it. And so this would be for N2, the N2 pressure, and the O2 pressure would be 0.38 ATM, right? Which when you add them up together is again going to be equal to, well, not that, it's going to be equal to this pressure here, ATM. All right, so you got to apply that to the fraction of the pressure, right? So here's written a little bit nicer here, right? So the mole fraction is going to be equal to the pressure fraction. So you calculate that mole fraction and you apply it to the total pressure, and you get the partial pressure of each of the gases, not a nitrogen or oxygen, right? You can also use PV equals nRT. I mean, there's always more than one way to figure this out, right? You could actually, instead of having 0.257, you could plug in 0.2 in here, and you would end up with this number here then, right? Same with oxygen, you would then end up with that number, and that only works because of Dalton's law of partial pressures. So sometimes you are going to work a problem where it will state such and such gas was collected over water, and when that happens, a little bit of water always mixes in with the gas collected. Like here we have the reaction of zinc. There's a piece of zinc that's put into HCl, and what happens, it turns into zinc chloride and hydrogen gas. Okay, so you need 2 of these, and when that happens, so you're generating this gas and you're capturing everything, you send it through a tube and collect it in some sort of vessel, beaker here, right? But because you're using this water so that none of the gas escapes, you actually have, water has some volatility depending on what temperature it is in. So the hotter that is, the more water molecules are going to evaporate, right? So you've got a little bit of evaporation, but you also have condensation. It's like this equilibrium between condensation and evaporation of these water molecules, and it's fairly insignificant, but that's where humidity comes from, right? You know, this water isn't boiling, but some of the water molecules that are moving faster than others have enough kinetic speed to vaporize, and then they also, when they slow down, they condense. But to make a long story short, is some water always mixes depending on the temperature of the gas or the water here, the room temperature. And you have to take that into consideration, because if you're only after the hydrogen gas, you need to subtract the partial pressure of water if you know what that is. And we know what that is from a table. Let me go look at this table here. And there's one in the book. This is a different one. But here it shows you the partial pressure of water at different temperatures. And so at room temperature, which is about 23.8 torr or millimeter mercury. So it's not very much, but you can look this up, but then you can compensate. So if you have if you use PV equals nRT, you know the volume and the temperature and the pressure, and you end not the pressure, but yeah, if you know the pressure, let's say it's 760 millimeter mercury, that's the total pressure, right? So again, it's Dalton's law of partial pressures, and so if I know what the pressure is, I can just subtract the partial pressure of water. So P H2O needs to be separated out if I want to know what P for hydrogen is. That goes back to this law here, of course. Gosh, all the way back here, right? The total pressure equals all the little pressures added up, right? Okay, so when you see a problem like this one here, what you look for is over water, right? So it's a stoichiometry problem. We have a piece of copper. We treat it with HCl, hydrochloric acid, and it generates hydrogen gas. So the following reaction, hydrogen gas is produced. When the reaction is completed, 57.9 milliliters of gas or hydrogen in this. Well, it's not hydrogen, it's hydrogen and water gas, right? So it doesn't say hydrogen, so that's indication number one, is collected over water. Okay, that means some water, depending on the temperature, is going to evaporate and mix in with the hydrogen gas, right? So you do have a mixture of, the total pressure is going to be equal to the pressure of hydrogen plus the pressure of water. And it also gives you a total pressure, so we know this. And we can look this up so we can solve for H, and then we can use PV equals nRT just like we normally would. So I already had this up here, but 22 degrees, we now have to subtract out 19.8 millimeter mercury from the pressure before we convert it to torr. But other than that, this problem works the same way. So I'm just going to bring up this problem, and then, because we're running out of time, but this volume was provided, the temperature was provided, you just had to convert it, and then we simply calculate the partial pressure of hydrogen by subtracting the total pressure minus the partial pressure of, and that's crucial that you do that or you're going to get it all wrong here, right? So this is going to be our adjusted pressure of hydrogen gas. So this is the one we want to use. And the question was how many grams of hydrogen are produced. And let me go back to the problem real quick. What is the mass? Okay, so they want to know the mass of hydrogen. So we can do this, either you can use PV equals nRT to solve for N, or you can again substitute molecular weight you can substitute that for N in, which is what I did here, and then solve for G. And so you've got the pressure. I had to convert this to torr, of course, but I need the partial pressure here, divide by 760, so that's partial pressure, the volume in liters, and then molecular weight of hydrogen. I calculated over here. Ideal gas constant is known, and then we multiply or divide by the temperature. Okay, so there are several good problems like this in the book. I highly recommend that you practice some of those before you tackle the exam. And there's one more lecture after this, and we are done.